Welcome to Approximating Propagated Error with Differentials. So the first thing here is just what is propagated error? So essentially, in the real world, when we take measurements, we're often not completely precise. Right? So in the real world, when we take measurements, we're usually a bit off. So for example, if we're measuring the length of a piece of wood, we might measure I don't know, 1.56 meters, when in reality, and it is really 1.561 meters. Right? So we measure, but we're not completely 100% precise. Let me give myself a little more room. And then that error in measurement will impact our calculations, say, for the volume of the piece of wood or the surface area of the piece of wood, etc. So that error in measurement will impact the accuracy of further calculations. So, for example, the surface area of the wood, how much paint is needed, right? So the error in this new calculation is going to be our propagated error, because it comes from an error in one measurement, but then it's passed forward through calculations. So the error in the resulting calculation is called propagated error. So we can put this kind of in terms of differentials. So going back through what I've already written, here we'd be setting x equals 1.56 meters, and our change in x is 0.001 meters. And then the error in measurement here, if surface area is our y, right? So the error will be our change in y. If surface area is our y, right, then the error would be our change in y. Right? Because we would really need the value at 1.561 meters for the length of the wood, but what we're going to calculate is the value at 1.56 meters. So we have a bit of an error there. So for an example, well, since that's change in y, we can therefore approximate the propagated error with dy, the differentials. So again, in our example, a company makes rubber balls of radius 2 centimeters. And the company is willing to accept an error in radius of plus or minus 0.01 centimeters. We want to know how large of a change in volume rubber used, how large of an error in volume is really what I should say. How large of an error in volume or the rubber used are they willing to accept? So we're supposed to give an approximation for the acceptable error in volume. So here we're looking at volume of a sphere. Right, so we have V is equal to 4/3 pi r cubed. We're interested in r equals 2 centimeters. And our change in r, or our dr, is plus or minus 0.01 centimeters. And so we're trying to approximate the change in volume, or which we can do by finding dV. So to do this, we need to find dV. And so we'll find the derivative of that volume function. So the derivative of the volume function, we have 4/3 pi times 3r squared, or 4 pi r squared. So dV is therefore 4 pi r squared times dr. Then we need to plug in. I'm going to give myself more room again. So if we go ahead and plug in, we again have r equals 2 centimeters, and dr is plus or minus 0.01 centimeters. So we have dV is equal to 4 pi times 2 squared times plus or minus 0.01. And we wind up getting plus or minus 0.5026. And so the error in volume is approximately 0.5026 cubic centimeters. So our acceptable error in volume is approximately plus or minus 0.5026 cubic centimeters. So from here, we can get into relative error. Relative error, we're essentially looking, want to see how large of an error is this in the context of the problem. So how large of an error is this given the measurements we are working with? And so what we'll do is we'll find relative error. So relative error is the essentially, in this case, it'll be that dV divided by the volume, specifically at what we measured. So our measurement would be 2 centimeters. So at R equals 2 centimeters. So again, we found that dV was plus or minus 0.5026 cubic centimeters. V at R equals 2 will be 4/3 pi times 2 cubed, which is 33.51 approximately cubic centimeters. And so our relative error will be that plus or minus 0.5026 divided by 33.51. Using the precise numbers from my calculator, I wind up with 0.015. And so this is plus or minus. And so we're essentially willing to accept a 1.5% error in volume. So the company is willing to accept a 1.5% plus or minus 1.5% error in volume. So again, we weren't precise here. We could have actually calculated at 2.01 centimeters, what is the volume? At 1.99 centimeters, what is the volume? And then found the precise error. And in all honesty, that wouldn't be all that much more work here than what we just found, and might be even less work. But this can be useful in more complicated calculations, particularly. So this is relative error, a way of measuring sort of how big of an error that is relative to the measurements we're working with. And this is how we can approximate our error using differentials.